Good. So my name is Johnny Chen. I'm the head of engineering here at Cohesity. I joined the company last November, and prior to that, I was at Google for 11 years. Worked on the ads backend, the ads fraud detection, and prior to coming here, I was in Google Research working on natural language processing. So Mohit talked about secondary storage, the issues with secondary storage, fragmentation, silos, copy data management problem. And he also talked about requirements. What does it take to consolidate that? And so for the remainder of this talk, we'll talk about how to translate those requirements into our implementation. Okay, this is the agenda of the technical talks. First, I will talk about a scale-out distributed architecture, a file system, how we handle mixed workloads, and our adaptive self-healer. Then I'll hand it off to Mark. He will talk about the architecture and a snap tree, how we do integrated backups and DevOps workflows, and then finally Abhijit will talk about analytics.
So I have a question. Just from the first moment I saw this machine.
Yes.
So you have 8 CPUs.
Yep.
And just 24 disks on the front end.
Yes.
And you told
just 12 disks on the front end.
12.
They're 3.5.
Yeah.
Okay, 12. So it doesn't look very dense, and actually secondary storage needs to be very dense.
So let's talk about this. Right, so
there
this
is something that I don't understand.
Okay, so this is a 2U chassis, right? 4 nodes per chassis. This is a 1 node, right? Dual CPUs, memory, SSD, 10 gig Ethernet, and yeah, we have 12 8 terabyte hard drives.
Yeah, but the CPU capacity ratio is not.
Let me answer that.
What can you do?
I think first of all, I'll say appearances are misleading. It's 96 terabytes of hard drive storage and some 6 terabytes of SSDs that are inside. Second, I think the CPUs are a little bit more because remember, this is supposed to do mixed workloads, not just backups. So we are also doing analytics on this. We're also doing DevOps on this, right? So there is compute needed on this platform. That's why we have a little bit more compute than storage. And remember also that this can scale infinitely, right?
So I think, for example, if I have an Hadoop workload of some kind, you run the Hadoop into the cluster.
Right. So
Top of the cluster.
yes. So we can potentially run a VM inside, which is going to be on our roadmap going forward, and then run Hadoop in that. Yes. But today we have in-place analytics that Abhijit is going to talk about, and there we run other kinds of analytics. And let's just defer that to the later part of this talk.
Okay. Sorry.
Okay. Good question.
But, I mean, to reinforce Enrico's point, there are primary storage systems designed to deliver very high performance with less CPU per gigabyte or less CPU per spindle than we're talking about here. You guys are providing a lot of compute for the amount of storage you have. I also want to say that I think that you're going to confuse the market by using the term secondary storage. Right. For those of us who are practitioners, primary storage is where data is created, and secondary storage is copies. And you're really saying for tier 2 applications, which is a different thing. And if we start mixing those metaphors, it's just going to lead to confusion.
Is that really for both, though, Howard, when you look at what their use cases are? I mean, they're talking about it I can see when you talk about backup and recovery, that's copies of data. When you talk about DevOps type stuff, that's copies of data. But when you start looking at some of the other things they had on the list.
Yeah, I was leaving those for when they got to them.
So let me take that. Howard, thank you for that question. We actually love the fact that people get confused by this because we actually want to redefine secondary storage so that people don't think of it as backups. People actually think that this can actually run some compute also. That's one. Second,
so you're looking forward to the heavy lifting.
Yep.
More power to you.
Second, I think what matters to customers is not how much compute is there. What matters to them is the actual value we can deliver to customers. And I can tell you that a dumb, old secondary storage device that just does backups, combine that with some other vendor from whom you buy backup software. If you compare that to this device, which is far more functional, we're actually significantly cheaper. So it's the value that matters, not what's in there. That's what the customers care about, right? So that.
Okay, thank you. Okay, so I'm going to talk about Oasis, which is our open architecture for scalable intelligent storage. So first, on our hardware platform, as we talked about, we have SSD and hard drives. And on top of that is our Oasis distributed file system. As Mohit mentioned, building a distributed file system is not easy. If it's easy, everybody would have one. And the reason it's hard is because these nodes, they're shared nothing architectures, and they can come in and out of the cluster. They can go up and down. And so the software has to be extremely intelligent to coordinate all these nodes to make them act as one coherent and consistent file system. So let's look at what's inside and some key elements in our file system. The first is a distributed lock manager. This is being used to do coordination and leader election. Second is a distributed NoSQL store. This is our distributed key value store. It's a strongly consistent key value store, and we build it in-house. A layer below that is the metadata manager. So this is a file system that manages directory structures and inodes. A blob store. Can you guys see that? Blob store. This is managing file level data. A data journal. This is an SSD-backed journal to absorb random I/O. A disk manager. This manages writing to the non-volatile memory. And then a Selfhealer, which is a background process that does things like garbage collection. Okay. And on top of that, we have the applications that Mohit talked about. Data protection, which is backup, restore, retention policies. DevOps, we expose NFS and SMB interfaces, so DevOps can use us as for their purposes and for filers.
Which versions of both?
NFS 3 and SMB 3 also. And analytics. So this is what we're talking about to eliminate our dark data. Okay. So a little bit about our file system. First is a shared nothing architecture, and it's a strongly consistent file system. So this is not like Amazon Dynamo, where it's a eventual consistent file system. And the reason it has to be strongly consistent is because enterprises need that kind of guarantees. Right? You can't run a database, a relational database on Dynamo. And there are no bottlenecks anywhere in the system. This is why we can do true scale out. We can scale infinitely.
Sorry.
Yes.
When you say infinite scale out, I've had that fair bit. What have you tested to? Are there numbers that you've got?
Right. So we'll show you a 32 node cluster.
Right.
And we can go more, but we just didn't want to buy so many machines just for this for this demo. And of course, Mohit mentioned incremental scale out. So you pay as you grow. It has to be
Wouldn't that be only around what, 8 petabytes? How many is that 32 node system?
So what is 96 times 8? Nearly a petabyte.
That's all you've tested to?
Well, that's
Yeah.
what we have resources for.
Yeah.
You can lend us some. We can
Hey, you're the one with $70 million.
spend it effectively.
Right. Okay. And as Mohit mentioned, this has to be highly available. If a node goes down, the system has to keep running. And he also mentioned in upgrades. So as we do non-disruptive upgrades, we can do kernel upgrades, firmware upgrades, and the file system will work without skipping a beat. And
So you use erasure coding or mirrored data, or
yeah, so we have a replication factor of 2. And because
How
of
do you-
these,
Sorry, how do you just going back to the point about infinitely scalable, how do you make sure that the network itself doesn't become the bottleneck to the platform?
that's a good
From an
question.
east-west traffic perspective, it's easy to go to, we talked about 32 nodes, it's easy to go to that in a single switch, but
Right.
once you start to scale out to 6428, what happens then?
So our architecture is within our nodes. So we have to sort of figure out, basically buy high-performing switches to make sure that there's no network bottlenecks.
So we do dual 10 gig per node, and so it's switched Ethernet. So it's not like all the traffic is going through some bottleneck of network. when two nodes are talking to each other, that's independent of when two other nodes talk to each other. So we kind of get
As long as they're on the same switch and you're not saturating an ISL.
So it's I guess your uplinks to your spine or whatever your network design happens to be is where your potential bottlenecks might be in east-west. Do you have the ability to, for example, try to keep traffic between multiple nodes on the same switches, and so therefore reducing the amount of traffic that's going via a distribution or a spine layer?
Right. We today don't do anything special there, but in the future we probably will kind of do something special for network also. But today we can imagine that just plug it into a 10 gig switch, make sure there's plenty of networking. We do peer-to-peer, and that's what we have.
So today, is it switches that you sell with the product, or is it a customer network?
If our customers ask, we do. We can sell either a Arista or a Cumulus switch along with the product, but some customers now already have 10 gig environments, so they don't need that.
And so most of our customers actually have 10 gig environments. Okay, and because of our architecture, you can scale linear in capacity and performance. So as you add more nodes, you add more capacity, and you also add more performance. Okay. Okay, so that was the scale out distributed file system. Now let me talk about how we support mixed workloads.
So before you go on, do the nodes have to be the same? Next generation nodes, can I intermingle, whatever comes next in hard drives?
Yes.
Okay.
Yeah. So this is the heterogeneous hardware requirement that we set for ourselves. So as Mohit mentioned, we want to have a converged secondary storage. So this means that we need to handle multiple workloads and concurrent workloads. So we need to have backup running at the same time some test and dev is being spun up, at the same time it's being used as a filer, at the same time we're doing some analytics. Okay? To do that, to handle those mixed workloads, and every workload needs different kind of requirements on a storage system. So if you think through what's required, it boils down to three basic things. One is we're gonna do metadata operations really well. So this is handling small files, dealing with directory structures, creating files, deleting files, and so forth. Second, we had to do data operations very well. So for sequential I/O, high sustained throughput. For random I/O, high IOPS. And third, we must have performance oscillation. So we don't want one huge backup job to completely starve out the other workloads. Any questions on this? Okay, so let me move on to file metadata operations.
So, having data protection and other ancillary storage in the same appliance, normally you want to have data protection on devices different than where the data is. That's why you have primary storage and secondary storage. But if I'm doing data analytics and file services and other things on this device, and I'm also doing data protection on this device,
Right.
don't you think there's an additional risk there?
So no. So a few things. One is when we do these additional workloads, we actually clone the system, so you never modify the existing file.
I'm okay with you isolating the data on the system. The problem is if there's a problem with the system, then you've lost the data.
So we have remote replication. It's coming, so we can.
And I'm okay with remote replication, but
if a bug in your file system decides to delete all the data, and all of your data is on 27 systems in 14 locations with your file system, that bug affects all of them. Right? This is a genetics problem.
Well, it's a classic problem.
If all you,
but that's not.
No, hang on. So we first of all we do remote replication, and yes, it's done to a Cohesity cluster, but we also do cloud archival, which is done on technologies like Google Nearline, which don't run our software. So if yes, we introduce a bug that kind of erases the software on all the data on lots and lots of data centers, we can always download it from the archive. So that's one. Second, I think maybe your question was more around, well, this is non-mission critical data. Do you really need an active copy for this? So that's where we feel run your primary. The primary is protected by us, and then whatever runs here, this is non-mission critical. It's okay to either remotely replicate it or to put stuff in the cloud.
Okay, so when you guys are talking about file services, you're talking about file services so that I can spin up copies of VMs so that I can use them for dev and test, not that all of my users' home directories are going to be on the system, right?
Depends on how you define mission critical. We have customers who want to put their home directories on us. They feel they can live with some downtime. But remember, with the remote replication and with cloud archival and stuff, it kind of gets minimized. So it depends on how our customers define that. But yes, if home directories are paramount, you need to be have them up all the time, then yes, you would probably put that in the primary system.
Well, it's not like there aren't customers who do snap and replicate. They do that today.
Yeah, but
Whether they should or shouldn't is irrelevant. They do it.
right.
Okay.
Okay.
And there's a risk for doing that, but if the company is 10, 15 years old and has had 10,000 machines in the field, the risk is somewhat minimal. If this company is 4 years old and it's got 1,000 machines in the field, the risk is somewhat higher.
I think you could say the same thing for primary storage companies.
Yeah, so that's why you have
Yeah,
that's why you have data protection of primary storage and take it off the
that's why
storage.
the fact that we don't trust anything is why you back up to something completely different from a different vendor than what your source was.
And that's the cloud for us.
Well, we're storage guys. We lose data. Companies go out of business. We don't have downtime. We have.
Yeah.
That's why I think
Data
I
loss.
think we all trust Google a little bit. So that's why we use Google.
I'm a steely-eyed storage guy. I trust no one.
Okay. Okay. Good questions. Okay, so let's talk about metadata operations. So here in this example, an app wants to create a file. So it talks to its local NFS client. It says, hey, go create a file on my Cohesity appliance. So the appliance asks the DNS server, give me the IP of the appliance. And let me talk a bit about, before I go into the details, let me talk a bit about how we do load balancing and fault tolerance using VIPs. So when we set up a cluster, say a 10-node cluster, each node gets an IP and also a virtual IP. And we register that virtual IP with the DNS of the cluster. Okay? So when the client asks the DNS, give me an IP for this host, the DNS is a round robin and hands out a virtual IP that belongs to one of these nodes. So this is how we do load balancing across nodes. Now when a node fails, let's say, so this client's targeted this node, let's say this node fails, somebody pulled the plug on the node, then we have a heartbeat mechanism that detects that the node has failed, and the virtual IP then migrates to another node. So this is how we do fault tolerance and load balancing. Questions on that?
Okay. And NFS client is your own design? And
No. So this is just
a normal standard NFS client.
Right. Yeah.
Is that the virtual interface? Is that provided by you, or are you relying on?
This is Linux provides this virtual IP interface. So you do ifconfig to get the virtual IP. Okay, now let's look inside the box to see how we actually do the metadata operation. So a create request comes in, it gets serviced by the NFS server. It forwards a request to a metadata manager. This manages the file system and the inodes. And so to create a file, you have to do two operations. One is create the file, then put the file in the directory when it was created. To do that, that is stored in our distributed NoSQL store that I mentioned earlier. And because these two operations have to happen all or nothing, so you got to have a transactional property, so we wrap that in a two-phase commit protocol. Once the two-phase commit protocol completes, it is acknowledged back to the metadata manager, and it goes back to the client, saying the files are created. And notice, because we have two-phase commit, if there's a failure in any of the steps, that the commit is rolled back. If you notice, what's interesting here is that this is purely distributed. There's no sort of single asset database. There's no single node that controls all the metadata operations. It's purely distributed, and this is how we can get true scale out. Okay, so now that you have the file created, now you want to write to this data. Now so let's go to the data path. So here, incoming data is coming into the system. The first thing we do is determine whether it is random I/O or sequential I/O. If it is random I/O, then we give it to our distributed data journal, which is backed by the SSD. Write to the journal and return success. So this is our fast path for random I/O. If we determine this is sequential I/O, then we give it to our blob store, which manages the blocks on disk. One of the things it does is it chunks up this incoming data into variable size chunks. And these chunks are our units of deduplication. And we use Rabin fingerprint to to determine the borders of these chunks so that we get maximum chunk deduplication. Okay? So for each of these chunks, we ask the global dedupe map, does this chunk exist in any of our nodes? Does it exist in any of the clusters? And if it returns true, we obviously don't write it. If it's not true, then we give the chunk to the disk manager, and it writes it to either the SSD or the HDD. And then we update the global map to say, hey, we have a new chunk and it's located here. And then once in a while, we flush the journal onto the blob store. Okay, so this is the write path. On the read path, we first check. So if you want to read a block, we first check the journal. If it's in a journal, we return it. If not, we look at the hard drive or the SSD and return that data. And one thing that we do, which is very unique, is that we do up-tiering. So if we detect that a block is being used heavily, either reads or writes, we move that to the SSD. Okay? So now it's serviced on the faster SSD. And so when a disk manager writes, if the data is hot and it's been on SSD, you write to the SSD. And if it's not, then you write onto the hard drive. Okay?
It's not really unique. That's what every hybrid vendor does.
So what's unique about it is, good question, is our patent pending tier optimized write scheme, or TOES. So what we do is when we write to HHD, the hard drive, we write out of place. Okay? So if you have lots of random writes, we sequentialize them and write out of place. But if the data is hot and it's on SSD, we actually write in place. And what this does is it gives us really good performance. So obviously writing out of place in a sequential fashion on disk is very efficient. And if the data is hot, you want to always write on SSD because that's just much faster than writing to disk.
Log structured file on HDD and random block placement on SSD.
Yeah.
It's log structured file like.
Like.
Yeah.
Right. And the other benefit is that you get much less fragmentation or garbage. So imagine if you're writing a block all the time, and if you write to hard drive, then you keep writing new blocks, and what you would have overwritten becomes garbage. So if you don't use write in place on SSD, you just create a lot of garbage as you write those blocks on hard drive.
But by the time you get past the SSD controller, you're creating, even if you're writing the same LBA on the SSD, you're creating garbage because it doesn't write. You can't overwrite in the flash.
So that's sort of the internals of Flash, right?
But from our metadata point of view, we don't have garbage. So from our distributed, the metadata stored in
you
our
don't have
node
file
system
system garbage. You just have flash system garbage.
That's
store.
right.
Yeah, flash system garbage. That's right.
But the Flash system garbage, Flash control takes care of that. Right?
Maintains it, yeah.
Yeah.
Well, some of them better than others.
True. Okay. Any questions on this?
Jumping back to the previous, what hash are you using for dedupe?
Okay.
And then are you just doing one single style?
So we use a SHA-1 hash. I think we use 20 byte fingerprints.
All right.
Okay.
And you assume that a unique hash means a unique duplicate hash means duplicate data.
Yes. So mathematically, I think
We're more likely to get killed by an asteroid
Actually,
in this meeting than that.
the
Than that
moon
to
will
be a
hit the Earth
problem.
before we get a collision,
because
right?
it's collidable now. Potentially collidable.
For intentionally collidable and deduplication collisions are completely unrelated problems.
So the probability is very, very low. Okay. All right. The last thing I'll talk about with regard to mixed workload is performance oscillation. So if you have mixed workloads coming into the system, you have a huge backup job, and now you want to spin up a test and dev. You don't want that test and dev to suffer because of this backup job. Right? So what we do is we have user-defined priorities and then user-defined workloads. So you can say for this workload, it's high priority QoS. For this workload, it's low priority. And what we do with that is we map that to a proportional resource allocation. So the way to think about it is if you had to do 10 things, you said, okay, the high priority thing, I would do 7 of your tasks and 3 of the lower priority tasks. Okay? And we have granular QoS throughout the system. To show you sort of how this works, so you saw this picture before. This is sort of our key components of our system. Just for illustrative purposes, let's say we have 3 queues here. Okay, we have a data protection job, a queue, a DevOps queue, and we look at a queue into the disk manager. In this scenario, let's say I have a huge backup job coming in. It's dumping 20 terabytes and just saturating the system. So all these queues, the queues fills up here, and the queue starts filling up here. Now somebody says, hey, I want to do a test in dev. I want to debug some problem. He spins up a VM and starts writing to it. If you didn't have QoS, that writes that's coming in would get queued behind all the write requests from the data protection job. But you have QoS, and you say this is higher priority, you essentially let it jump in front of the queue. You let it cut in line. And so now you can have responsive DevOps at the same time, have the data protection run as fast as it can.
So what are the knobs I get to turn for QoS?
So we'll show you this in the UI. We want to make it really simple. So basically we say, is it high or low? Is it random or is it backup jobs?
So the architecture actually supports doing proportional shared scheduling, so you can actually assign weights. Our UI right now is very simple, high, low, that sort of stuff. We'll wait for feedback from our customers if more is needed. Right. So that's why we have it like that.
But underlying system is actually a lot more complex than what I just showed you, obviously.
One should only hope.
Yes. And but on the UI, we're trying to make it as simple as possible, and then we'll see what the customer feedback is.
What's the greatest number of files you've put into one of your systems? How many billions?
I don't know the answer. We have loaded.
We have loaded
hundreds
of more than 100 terabytes of data.
I'm not sure how many.
But I don't know how many files. Probably, I don't know, close to like several hundred millions, but don't know if we
no
reached
billion level.
I think bulk of our tasks have more been on kind of the VMware backup side, so that's kind of pulling more data than pulling files. Mm-hmm. But we scale. We are not limited to a few thousand files or a few tens of thousands of files. Again, it's
I'm talking billions of files being a small to mid in like bioimaging, things like that.
There is nothing.
And that would be secondary level. So
there is nothing in our architecture that prevents us from creating a billion files. Testing is another thing.
Yeah, so we haven't tested it. Good point, and that's something that we will do. But we have loaded over several hundred terabytes into our system. Okay, so the last thing I'll talk about is Selfhealer. So in traditional, actually in modern file systems, a lot of operations are done offline. So even in the Unix file system, when you delete a file, that the operation returns quickly, but the data blocks are reclaimed at a later time. That's called garbage collection. In a distributed system, you have garbage collection, but you have a lot more things you have to do in terms of healing the system. So our garbage collection or Selfhealer is a distributed process. It's based on a MapReduce framework. So it does things like garbage collection, but it also does things like disk rebalancing. So for example, if I add some new nodes to the cluster, I want to now distribute the data onto those new nodes. Okay? This gives me higher read and write performance. Or if a node goes down, now I need to replicate the data that was on that node to the other nodes. The other thing we do with Selfhealer is post-process actions. So for example, if you want to turn on encryption or compression on a file system, we don't need to do it immediately. We can do it in the background. And of course, this system has to be fault tolerant. So if a node goes down, we can't just say, hey, sorry, I can't heal the system. It has to continue. And so if a node goes down, we'll heal the other nodes that are still up. And more importantly, well, and just as important, is it's continuous and is run on a low QoS. Okay? So the healing is always running in the background, but at low priority. So if there are user jobs running, it takes lower precedence. If the system's idle, then it ramps up. And this is actually very important. We have a client that has a lot of data, and they have a very popular target storage vendor, and he tells us that they run backup 6 days a week. On Wednesdays is garbage collection day. So they actually stop all their jobs to do garbage collection for Wednesday and then continue from there on. And for us, that's not acceptable. As a converged solution, we can't tell the business guy you don't get analytics on Wednesdays, or we can't tell the DevOps person you can't do any development on Wednesdays. So for us, it has to operate all the time. Okay, so this concludes my section. Any questions?
I think your deduplication, am I right in saying you can do inline or post-process?
Yes.
What would be the different use cases? And if you're using inline, is there a point where, say, under high load, it would actually fail over to becoming post-process anyway?
So you would want to do post-process or sometimes no dedupe if you're running a test dev environment. Right? There's no need to dedupe that because you're going to do rather render writes and you can throw everything away.
Well, that and you're doing I/O to spinning disks, and I/O to deduped spinning disks is no fun at all because it's all random.
Well, if it's random, it hits our data journal, which is absorbed by the SSD.
No, but if I'm trying to read deduped data sequentially, the disk drives still see random I/O.
Yeah, the difference is that if the working set fits in your SSD, we will have moved that stuff into the SSD because of our up-tiering. Mm-hmm. But like Johnny said, we do both inline as well as post-process dedupe. Very likely for test and dev, it makes more sense to do post-process because one of the things is you probably are also overwriting the same thing again and again. You don't want to deduplicate and then rewrite it, deduplicate and then rewrite it. So you probably want to use post-process. But when it comes to backups, it's your choice. You can use inline or post-process. It's as efficient.
And what's the dedupe granularity?
It's 8K to 16K. So that's the variation.
And the post-process is done by the self-healing algorithm that I just spoke about.